Okay, so let's start with the today webinar. We are gonna have a seminar by Ronan McAdam on monitoring and forecasting marine heat waves here today. I'm Enrico Scoccimarro. I'm going to moderate this talk. I'll have to spend a few words about CMCC before starting. Just give me a couple of minutes. As you know, the CMCC is a research foundation with the aim to investigate our climate system in terms of variability and change. And this is something that we used to do mainly through models, climate models, but also through impact models to provide useful information and reliable information to the policymakers and different stakeholders. The foundation is active in different places over Italy. You see here 7 different locations in which we are working with our 11 division at CMCC. There are many members and institutional partners together with the Ca' Foscari University, University of Sassari, Lattuca, and University of Bologna. There are also the National Institute of Geophysics, the Italian Aerospace Research Center, and the Polytechnic University of Milan. Last, the Research for the Future is part of this group of partners. Our activities are mainly active through 11 divisions. As I said before, there are not only divisions devoted to the study of the climate variability and change in terms of physics, so the ocean and the atmosphere, the global and the regional scale, but also there are division devoted to the analysis of different impacts on agriculture, forest, and economy, and risk assessment, and so on and so forth. Our activity are mainly performed through modeling. That means that we use numerical models, and this is something that needs the support of the Advanced Scientific Computation division also. And our activity are mainly running on our supercomputing center. The new one is now available at in Lecce, and these are a few characteristics of the computer. But just to say that since we mainly work with models, we need high power resources, and every 4 or 5 years there is the need to improve our computing system to be useful for our activities. So whatever we do is also communicated and disseminated through different activities, not only within the single European project in which we are involved, but also through specific activities like the one that you are participating now. So, for instance, this webinar is part of the outreach activity that we used to do at CMCC. You are all muted if I got it right, and there are 2 ways to interact with the speaker at the end of the talk. So he's going to have 30 minutes of talk, more or less, and then you will have the possibility to ask questions. You can do that through the question and answer section, writing your questions, and then we will try to. I'll read the questions to the speaker, and he will try to answer you. And also, you can raise your hand. It depends on the way you prefer, writing or just having a chat. So this is more or less all from my side. Do not forget to follow our social medias. There are many of them, plenty of them: Twitter, Facebook, Instagram, and whatever. So Ronan, can you hear me?
Yes, loud and clear.
Okay, so as I said, Ronan McAdam is our speaker today, and he is going to talk about monitoring and forecasting marine heat waves. Ronan is a colleague since, I would say, 4 years, if I'm not wrong, here at CMCC, after his PhD in oceanography that he got at the Imperial College in London. He joined us and has been really active in different activities, such as the testing and the maintenance of different tools that we have here, like the seasonal prediction system and the global ocean reanalysis, together with many other Copernicus Marine Services dataset. The main topic of this talk is on heat waves, and this is something, marine heat waves, that is a really hot so sorry for the word, topic that is also very well mentioned in the most the high-ranking journals that are publishing a lot on this topic in the last couple of years. So, Ronan, the floor is yours. Please, you have 30 minutes. I'm gonna stop the sharing. Let's share your screen, and I'm muting me.
Thank you very much, Enrico. I am sharing my screen, and I hope you can see it. So I thank everyone, first of all, for I thank everyone for joining today. I'm very happy to have a lot of people here to hear some words about marine heat waves, which, as Enrico has mentioned, are a very important topic now. Their profound societal impacts are being measured and understood. And we at the CMCC are in a good place to study them because we are, as you've heard, producers of models and forecasts, which can help us monitor and forecast their occurrence. And so that's what we're going to hear about today. So first of all, I'm going to obviously introduce what marine heat waves are, a bit about their background. Then I'm going to zoom into a particular event, a record-breaking event, which occurred only a few months ago in the Mediterranean Sea, and discuss with you the actually successful attempts of the CMCC's short-term forecasting system to track it. Then we will look back into the past few decades with reconstructions of the ocean to understand the marine heat wave's long-term characteristics and trends, particularly focusing on local scale and subsurface events as well. And lastly, I will finish with some exciting work, I believe, on seasonal forecasting. So in April and May, can we make predictions of the summer months, June, July, August, and make predictions of marine heat waves which are to come? So first of all, let's get familiar with marine heat waves. I think we're all familiar with land-based heat waves, which we experience every summer now, unfortunately, and other extreme events like hurricanes and storms, which I think when I say those words, vivid images come to mind of destruction and damage. But with marine heat waves, perhaps most people in the audience don't have that imagery yet. So let's try and familiarize you with these events. Here is an atlas, let's say, of the most infamous events on record, some of the most intense and the most long-lasting. And what we have close to home, well, for us in Italy anyway, in 2003, in the summer, in the Mediterranean, we had what was, according to this study, the most intense record, heat wave on record, reaching up between 4 and 5 degrees Celsius above the average conditions. And on the other end of the scale, you have very long events, such as those which occurred in the Northeast Pacific and Alaska in the mid-2010s, which lasted up to 18 months. Now, for all of these events, there are many studies on their impacts on wildlife, such as mass mortality, the influence on disease spreading. And of course, similar impacts have been found for industries such as fisheries and aquaculture farms. But it's not a simple case of heat bad or heat kills. There are nuances and subtleties to these socioeconomic impacts. And I'll share a few with you here now. For example, this very long event in the Northeast Pacific saw extreme declines in the nutritional value of forage fish, which in turn are eaten by salmon, which in turn are eaten by us. And this study believed the long-term extreme heat caused significant damage to the ecosystem, resulting in this nutritional value decrease. In 2003 in the Mediterranean, we actually had some quite vivid imagery here of either completely dead coral reefs, partially dead, or coral reefs which were more susceptible to disease. And interestingly, here in Northwest Atlantic in 2012, this extreme heat led to a record amount of lobsters being able to be fished and farmed, which sounds like a wonderful thing for the local economy. It extended the fishing season, and as I say, there were record landings. But this extreme heat led to extreme supply, which was not matched by extreme demand, and that in turn led to a price collapse. So the knowledge needed on marine heat waves is very important for many reasons. What potential stakeholders do with that knowledge is not quite the scope of this talk. That's a very complex question, as you can see here. But we, the CMCC, as a provider of models and forecasts, need to be sure that our products are telling some truth or providing some useful information. So first of all, we need to define marine heat waves. And the classic, well, the now classic definition is that a marine heat wave is an anomalously warm event which lasts for 5 or more days. Anomalously warm means temperatures warmer than the 90th percentile, and it's recommended to use a 30-year historical baseline period to calculate this threshold. And as we'll see today, 30 years is not always possible depending on the data set you're using. And so once you, with this definition, you can determine the duration of a heat wave, you can determine the peak intensity, the average intensity, and I should say the intensity is the temperature above the threshold. And with those characteristics, I'll call them, you can determine seasonal and annual characteristics like the frequency or the number of events, the total number of days, or you can pick apart the strongest intensity events. Now, as we've seen, these marine heat waves, they last at least 5 days and they can go for as long as 18 months, perhaps more in the future. And that's because what drives them, the processes which cause them, from air-sea heat fluxes to long-term climate change, they cover a range of temporal and spatial scales, and they all interact with each other to make the problem even more complex. So whatever products we produce, we need to be able to capture processes on all these scales. And whatever products we do produce need to be verified against what we believe to be the truth. And what we believe to be the truth when it comes to marine heat wave comes from satellite data, in particular sea surface temperature from satellites. We have data sets at global scale and regional scale, and they're typically provided freely on various climate services, as we'll see. Here at the CMCC, especially at the Oder division in Bologna, we produce reanalyses of the ocean. Reanalyses are three-dimensional reconstructions of the ocean, typically over the past few decades. And these are built from assimilating in situ or satellite observations of the ocean into a hydrodynamical model to create the best estimate of the current state of the ocean or the past state of the ocean. And we at CMCC produce global and regional reanalyses. We also produce various forecasting systems. In this talk, I'm going to introduce the short-term Mediterranean forecasting system and the global seasonal prediction system. And all of these tools will be useful in the understanding and the tracking of marine heat waves. And all of them are freely available on the various Copernicus services. Now let's zoom into a particular event. Only a few months ago in the Mediterranean Sea, at the CMCC, we saw in early May that there was a marine heat wave beginning, and we decided to track it using our using satellite data and our short-term forecasting system. And after our efforts, this actually made the news. Now, I don't know if marine heat waves have ever made the news before, surely they have, but I don't remember them being on page 6 of Le Monde, a national French newspaper. They asked for our input for a full-page spread on the Mediterranean heat wave at the time. So we gave some information, and they and others approached us because of the analysis I'm going to show you now. So first of all, I'm going to show you a description of the event with satellite data of the Mediterranean Sea. We have very high resolution, 0.05 degree, daily SST, of course. And what I'm showing at the top right for this year, from May onwards, is the anomaly. So that's the temperature above climatological conditions for the areas which are experiencing a marine heat wave, or which were experiencing a marine heat wave. And we see in May, the marine heat wave was largely constrained to the Western Mediterranean, but it eventually, I think May is just starting now, I can't quite see. But yes, it does occasionally spread into the central and eastern parts of the Mediterranean throughout the summer, while lingering in the Western Mediterranean with anomalies up to 6 degrees. For a summer scale view of this event, and to be able to compare it to others, I've calculated here the activity, which is the integral of the anomaly and the area of the event. And you can see that 2002 compares to this infamous event of 2003 in terms of the peak activities reached and the duration of the events on the basin scale. In fact, May and September for 2022 was much more exceptional than the previous events, which were considered the most exceptional. So we're dealing with a very exceptional event here. Now, we didn't just describe it with satellite data, but we also tracked it with our forecasting system, which is a contribution to the Copernicus Marine Service. It's a high resolution hydrodynamical model which provides 10-day forecasts and also is used to determine an analysis of the previous 2 years, which initializes the forecast. With that, we can produce maps such as this, made at the end of July, of 3 to 4 days in advance, for example, which tell us what the anomaly will be. And in this case, I've plotted also a red contour to show the boundary of the marine heat wave. So we can see all the small scale features evolving as well. We have yet to do a full rigorous validation of this forecasting system, but we have found encouraging results by comparing to temperatures in specific regions. Here in the Ligurian Sea, we found that our forecasts in blue captured the onsets and decays and the peaks and so on of the marine heat wave, which is the ground truth is shown in the light gray. And in the red, I should say, we're looking at the average climatological value, and in the dashed red is the threshold. We can see similarly encouraging results for the Gulf of Taranto, which experienced a different side to this marine heat wave, shorter duration and few sharper peaks, but nonetheless, our forecast system captured these peaks and these decays. So encouraging so far, but now we're going to look not just at the short term and the most recent event, but we're going to look long term. We're going to look at characteristics and trends of marine heat waves. And for the moment, we're still focusing on the Mediterranean. So we asked ourselves, do CMCC's reanalysis recreate observed marine heat wave characteristics? And we're not just talking about 1 year, we're talking about several decades, well, 3 decades in this case. So what we've done in this study, which is available in the Copernicus Ocean State Report, is compared the satellite-derived sea surface temperature, which I've just described, to 2 reanalyses. And as I mentioned earlier, reanalyses are reconstructions of the ocean. And we have a regional high-resolution reanalysis, again, produced here at the CMCC. We're talking about 4 to 5 degrees resolution, 4 to 5 kilometers resolution, with 141 spaced vertical levels. And we compare that to a global reanalysis, which has some important differences, not just the resolution, which here is 1/4 degree, but the fact that this GREP product, as it's called, is an ensemble of 4 reanalyses, which allows us to quantify uncertainty in our estimates of the ocean state. So we're comparing these 2 reanalyses to see, also as a test, to see how good GREP is in our basin level. We're looking at a study period of 93 to 2019, with a climatology period of 93 to 2016. So to do this, we have split the Mediterranean into 4 different sections, which is justifiable, not just because of their geographic shape, but also because of the biological activity and the range of biodiversity in each of these basins, which is to some degree made clear by the average chlorophyll concentrations. And so what we did for each of the data sets, we compared the number, the average duration, and the maximum intensity of the basin, which you can see in A, B, and C plots here, basin average, and then we look at the trends of the different subsections here. And what we find is that for the number of events, there is a good agreement in all data sets on the interannual variability. But for the duration, we find that our reanalysis typically overestimate the duration of events, but nonetheless capture the interannual variability. For example, 2003, as we've heard, a sharp peak in both duration and intensity. We also find that our reanalysis underestimate the intensity of marine heat waves, which is actually typical of lower resolution models, but it's interesting to see that we're finding this behavior for a very high resolution model too. By and large, as I've said, GREP, the lower resolution reanalysis, captures the interannual variability and doesn't disagree significantly from many of the trends, but in some cases it does. And we usually see that the trends agree well between the satellite data and the reanalysis, the high resolution reanalysis, that is. So semi-encouraging results for the two reanalysis there. Beyond that, we have made a move towards stakeholder relevant information. So it's all well and good for us to understand our models, but we need to package the information they provide in a meaningful way. And what we've done in a study, which is coming out very soon in Frontiers in Marine Science, is to take the exclusive economic zones shown here in the map and to calculate the marine heatwave characteristics and trends for each one. Which is a pragmatic approach to this analysis, but we also include subsurface marine heatwave information. And we propose not to use a specific level of temperature, like 10 meters or 20 meters, but to use the ocean heat content, which covers a range of depths. And the motivation for doing that is quite simple. Whether it's a plankton or a large predatory fish, there is large vertical motion throughout the ocean. In this case, several times per day, between 0 and 80 meters. This is, I think, a tiger shark in Western Australia. So we're going to look at the surface and subsurface marine heatwave information for EEZs. And we always talk in oceanography about zooming into local scales and providing information on local scales, because ocean processes are, indeed, there are many local ones, of course, especially in the Mediterranean, and we see that in the differences in the trends of sea surface temperature and ocean heat content. So we are justified in using a local scale, and we think in terms of the science, and we're justified in using EEZs for creating what we think would be a national narrative for oceanographic results and dealing with stakeholders. And for marine heat waves, that turns out to be very important. What we see here at the top, 2-time series for one of the Spanish subsections of the EEZ. And in 2003, again, we see this very intense, long-lasting marine heat wave at the surface, and we see no signal for it when you consider the upper 100 meters. On the other hand, in 2016, in the Egyptian EEZ, there was indeed 2 surface marine heat waves, which when considered the subsurface, turned out to be one long-lasting event. So information on both is necessary for each country and for stakeholders in each country. What we're going to do now is have a little look at the depth section of marine heat wave characteristics to understand how they change with depth. So I take this cross section, which covers the Tunisian, Libyan, Greek, Cyprus, and Lebanon EEZ. And we have here the mean characteristics for a range of marine heat wave indicators. And what I'd like to point out, first of all, are the general patterns. For example, the duration of marine heat waves typically increases with depth, which is not a surprising result for us oceanographers, given that the variability at depth decreases. So any extreme events are expected to be slow changing and longer lasting. Likewise, with the intensity events, they are weaker generally below the surface. But there are, in this case, interesting exceptions to that. We see, for example, the duration, surface level durations, which are relatively short, about 15 days, extend into 200, 300 meters in, I believe that's the Greek EEZ. And intensity, on the other hand, has a peak between roughly 25 and 200, 150 meters, not connected to the surface ocean. So we have interesting vertical dynamics here playing a role on the marine heatwave characteristics, which need to be studied specifically. And there are similar stories for the trend, the changes in these characteristics. What we see at the surface is not the same at all as what we see at the subsurface. So there's a whole heap of information there. We want to, as we say, repackage that for an EEZ approach. So we can take figures like this, which is all the mean and the trend on the right of surface marine heatwave characteristics. And what we've done is just take a very simple top 10 league table. And in this case, I'm just showing you the mean surface duration by EEZ. So in this case, we could say that in general, Israel typically has the longest marine heat waves, and in second place, Egypt, and so on and so on. And that's useful, but when you look at different characteristics, if I looked at intensity or number, then the league table would be different. So it's not about which EEZ is worst off, it's about how marine heat waves affect each national waters differently. We can repeat this to make the point even clearer for the subsurface, and I add in the top 10 for the subsurface durations at the bottom. And you see that the order of our league table changes, and there are actually some new additions. So Western Greece, for example, which didn't previously appear on the top 10 duration, does when you consider the subsurface. So we really think we've justified using an additional marine heat wave methodology here. So that's been a look at the past. And I think that's important. The main point from that is that we want to interact with stakeholders. We often don't know what the stakeholders want. They may want many things. Fish farms, for example, want different information than marine protected areas. The use of EEZs allows us to have a national scale look at the trends and the characteristics, allowing us to zoom in. And that discussion of stakeholder desire remains on our mind when we're talking about forecasting. Seasonal forecasting is a very important tool already for the energy sector, the agriculture sector. We want to see similar use in the ocean environment as well. So for those uninitiated in seasonal forecasting, as the name suggests, we can make forecasts of the coming seasons, the coming 6 months ahead. And these, in the case of the Copernicus seasonal forecasts, are freely available. So what you could do is go online and download or have a look at a map of forecast of SST anomaly. So this is the SST above the average climatological conditions. This case, we see May forecast of the summer months this year, 2022. So we can actually see that this year in the Mediterranean, warmer than average conditions were predicted. But were those warmer than average conditions actually marine heat waves or not? And that's what we have attempted to answer in this part of the study. So we're using our in-house seasonal prediction system, SPS 3.5, which contributes to the Copernicus Climate Change Service. This is a 6-month forecasting system. So we have forecasts of 6 months. We have an ensemble of 40 members for the past period. And in this case, we have data available from 93 to 2016, which is unfortunately lower than what is recommended for marine heatwave studies, but that is what we are constrained to use. And as you can see here, a seasonal forecast system is built from full coupling between Earth system components. And I'll point out here we have an atmospheric resolution of 0.5 degrees and an oceanic horizontal resolution of 0.25 degrees. So to validate the seasonal forecast system, to have a benchmark of the truth of 20, 30 years of data for the subsurface ocean, as we've seen, we cannot rely on satellite data. We need to use reanalysis to understand what's going on below the surface. So what I'm doing here is showing our average marine heat wave characteristics, which we've seen for the Mediterranean in other data sets, but I'm showing them here globally. And we find actually similar findings. So the subsurface marine heat waves, which we define as the upper 40 meters ocean heat content, there are typically fewer events. And these events are typically longer in duration and less intense. And this is true, largely speaking, on a global scale. So we take these marine heat wave characteristics, number, duration, intensity, and we're going to turn them into forecasting indicators, such as the number of marine heat wave days in a target season, the strongest intensity event, or the number of events. And we do that because unlike the short-term forecasting system, which can predict the more precise arrival of a marine heat wave in the coming days, seasonal forecasts can't do that. They can't tell you in 5 Tuesdays' time there's going to be a marine heat wave. they can tell you more the average conditions, and these forecasting indicators are in a way average conditions of marine heatwave activity. So we're talking about propensity for there to be events rather than the precision or the precise timing of events. And specifically here, we're looking at summer marine heat waves. For the Northern Hemisphere, of course, summer means mid-May to end of August. And in the Southern Hemisphere, we have mid-November to the end of February. And we're initializing our forecasts in May and November for the respective periods and removing the first 2-week period. And now the final data set I have to introduce to you is the global version of the satellite-derived temperatures we saw earlier for the Mediterranean. Very similar, slight difference in the data that they use to create this product. And we're going to use that to compare marine heat waves at the surface and at the subsurface as they occurred in real life, or according to the truth of the satellite data and the reanalysis, and what we predicted with the seasonal forecasting systems. So what we have here on the left, the satellite data, the number of marine heat wave days in the Northeastern Pacific in 2014. And at the bottom, we have the subsurface data from the reanalysis. And on the right, we have the forecasts of these events. Forecasts made in May of the May, June, July, August season. And what we find is that the pattern agrees very well. There is some underestimation in the magnitude from the forecasts. And we also find that the subsurface marine heat wave conditions persisted longer than the surface marine heat wave conditions. If we look at the full record now, 93 to 2016, at the top we see the surface compared to observations, and the box and whisker diagrams show the ensemble of the forecasts. And we find there is a good skill in capturing the interannual variability, the relative peaks. And we find the same for the subsurface. We find also a slight increase in the correlation value between the ensemble median and the validation data sets. So it's encouraging. It's good news for the Northeast Pacific. And now we look at the Mediterranean in 2003, again, our infamous event. And we see a different story here. So in 2003, as we've said, in the subsurface, the event did not extend as wide as at the surface. And the forecasts did quite a poor job of capturing the marine heat wave conditions at the surface, severe underestimation. And in the subsurface, the forecasts to some degree captured the positioning, but again, underestimating the number of days. And typically in the Mediterranean, the eastern side is more predictable than the western side for a range of variables, including the temperature and the heat of the ocean. So what we're showing here is the record for the Eastern Mediterranean. And you'll find at the surface, of course, 2003 is sticking out in terms of number of days. And actually the forecasts do a pretty poor job. They're quite unreliable because every year they say there's going to be a small amount of marine heat wave activity, even in years when there is relative peaks. Whereas at the subsurface, we see an enormous and significant increase in the skill, and that's denoted by the correlation and the root mean squared error. And the fact that many of the marine heat waves occurred more recently and did not occur, such as in 2003. So we want to know if this increase in skill is global, or are we looking at specific regions only? So what we've done is taken the correlation skill score of a range of indicators, so the number of marine heat wave days, the strongest intensity, and the number of events. And this is for the subsurface. And what I've done is masked out any insignificant skill. So what we find is that actually in the tropics, there are large parts of the ocean in which we can make good predictions of marine heat wave indicators for the subsurface. Less so in the mid-latitudes, beyond 30 North and 30 South, but nonetheless, we see the Eastern Mediterranean, parts of the Northeast Pacific, and even parts of the Southern Pacific, Southern Ocean, in which skill is significantly high. We typically find, for example, that number of events is harder to predict. So that depends a bit more on capturing the day-to-day variability, which is harder to do for a seasonal forecasting system. But we are encouraged by these results on a global scale. Now I'm going to compare the subsurface skill with the surface skill. And what we see here in red is where the subsurface marine heat waves were more accurately predicted than the surface marine heat waves. And again, we see in red the Eastern Mediterranean and parts of the Northeast Pacific, which you've already seen examples of. And it depends more now on what indicator you use. For the number of marine heat wave days, actually in the tropics, we find that surface events are more accurately predicted in some places, but by and large, the skill of both is high. So I'm not too worried about looking at these blue regions. In the mid-latitudes, we see where the subsurface events are easier to predict. We see more red. And we see particularly that the intensity is easier to predict for the subsurface. So we find this a very encouraging result. So not only is subsurface marine heat wave indicators perhaps more relevant to stakeholders, but perhaps more predictable because of the naturally lower variability of the variable we use to denote them. So we're very encouraged by these results, but I wouldn't have got these results without a whole lot of help from many people. And indeed, many of the data sets I've been lucky enough to use for this study are developed by teams of dozens of people in the CMCC and otherwise. And I use this slide to thank them all and to thank my collaborators, in particular Simona Messina, with whom all of this work was created, and also collaborators in the EuroSea project, which has been the main source of funding for this work. So I will come to an end now and remind you of the key take-home messages. We at the CMCC produce a range of reanalyses and forecasts which are used to track marine heat waves, and we do that on a range of spatial and temporal scales. In the Mediterranean recently, we had one of the largest and most intense record marine heat waves, and we were able to capture the behavior of that marine heat wave with our short-term forecasts. We've introduced national scale marine heat wave indicators, which we think can be used as a narrative to get nations to strengthen their observing systems and to establish local scale risk assessments specific to the context in which they find themselves in. And we've done a lot of work on subsurface extremes, looking at general patterns and also highlighting particular exceptions where perhaps we need to study processes like vertical advection and how they affect marine heat waves. And as we've just seen, seasonal forecasting of marine heat waves is most certainly viable, even in the mid-latitudes. And subsurface indicators may well be easier to predict, not just more useful than the commonly used surface indicators. With that, I thank everyone for your attention, and I look forward to the many questions from you. Thank you very much.
Thank you, Ronan. Really nice presentation, clear and sounding. We have already a list of questions. I think that we can start from the bottom. Emily is asking, when comparing the duration and intensity of marine heat waves with different configuration of your analysis, are the resolution in the ocean and the atmosphere different?
Well, the reanalysis we're using is an ocean reanalysis. So I suppose the question would be, what's the difference in the data used to force? And I'm going to get this wrong, but they are both based on ERA, and I think the Mediterranean reanalysis is using ERA 5, and GREP, the global reanalysis, is using ERA interim, soon to be updated. But this is a good question that would require a proper inter-model comparison. You know, taking a model and just changing the forcing and see what difference that makes. We've been a bit more pragmatic in looking at whether our different reanalysis are good enough compared to the satellite data, but we haven't quite understood if that the difference in quality, let's say, comes from the atmosphere or the ocean component, etc.
Okay, thank you. And there is also a comment from Carla. If this is not already the case, shouldn't the negotiators or decision makers with regard to climate and biodiversity protection also be urgently understood as stakeholders? Or yes. If this is already happening, in what way is this happening?
Absolutely. What I'm showing today is not a replacement to engaging with stakeholders directly. It's the point is that maybe I didn't make this clear enough, but there are many stakeholders of the ocean, of the marine environment, with different needs from us and from, you know, they have different requirements. Before doing that, we wanted to produce this sort of local scale study specific to EEZs, but absolutely we hope to work specifically with individual stakeholders, such as aquaculture farms, and to understand what their idea of a marine heatwave tracking tool would look like, what would be most useful to them. That is ongoing, and actually in the EuroSea project I've talked about, there is work ongoing with specific aquaculture farms, for example. But now we feel confident that we are armed with good knowledge of our products and our tools. So it's an absolutely vital next step.
Okay, thank you. From Dorothea, is there any particular reason to have a global analysis that does not include polar regions? She's referring to the pictures that were without the poles in your slides. It is well known that marine heat waves in the Arctic Ocean, for instance, have been as strong as in other ocean basins. Are they more difficult to be detected in models?
No, we shamefully perhaps, but we chose to take out the polar regions and the subpolar regions from our analysis for the sake of simplicity, let's say. There are indeed studies on marine heat waves in the Arctic regions, but I don't know on the differences between models capturing marine heat waves in those regions and forecast systems, for example. And in the case of forecasting systems, you'd have to consider obviously the biases in sea ice coverage, etc., and how you would define a marine heat wave in the presence of sea ice as well. I know that's a point of contention in some of the literature.
Okay, so let me go ahead because there are many questions. So the next one is by Antonietta. What determined the evolution of the 2022 marine heat waves from the western to the eastern part of the basin? Shifts in atmospheric forcing or ocean advection?
Yes, that's a very important question, and one I skipped over, but it is something we're starting to look at. We don't know for sure because we haven't measured everything, but we have found signals of atmospheric forcing, which cover mostly the Western Mediterranean. And when those shifts in, for example, looking at the geopotential height contours coming from the African continent, bringing warm air, they typically covered the Western Mediterranean and occasionally shifted eastward. So it seems to be largely due, at least in the case of 2022, to these atmospheric forcings. But I wouldn't say for sure because we haven't looked at the effect of ocean advection yet.
Okay, thank you. Another question from Russia. Thinking at the global scale, as temperature continue to warm, do you see any new areas that may become susceptible to marine heat waves? I'm thinking of areas like the Gulf of Thailand.
Oh, that's a very good question. I haven't looked at areas in which some of these areas, but in the trends we've seen in marine heat waves in some cases in other literature have been attributed to anthropogenic climate change, but there is generally a warming trend in the literature in many places, so it plays a role. I'm not sure if in some of these cases, like in the Gulf of Thailand, if there have been events previously in the record, like in the Mediterranean in 2003, that was a very extreme event which occurs in the middle of our record, so it's in that sense is not fully attributable to climate change. This would require I guess a location by location study of the specific events.
Okay, so there are also many thanks from different people, but this is from Branco. In terms of sea dynamics and marine heat waves, does the internal Rossby wave radius of the formation shrinks or it grows?
Could you repeat the question, please? Sorry.
Yes, in terms of sea dynamics and marine heat waves, does the internal Rossby radius of the formation shrinks or it grows?
I'm not sure I fully understand the question, to be honest. Is perhaps the question where marine heat waves are more frequent? Or
maybe we will have to start a discussion live on writing later. I mean, you can get in touch with Franco. I want to go ahead.
Yeah,
because there are many others.
Yes.
There is one from Carla again. To what extent might these heat waves also affect the ability of the ocean to produce oxygen? As far as I know, every second breath comes from the ocean, right?
Ooh, excellent question. A bit out of my field, into biogeochemistry there. There has actually been a study on how extreme warming events affect the uptake of CO2. So there is a link there between that process, different process, of course, but it's starting to be done. I'm afraid I'm going to have to answer, I don't know. But there are also studies on compound events. So when there is a reduction in oxygen and a co-occurring with an increase in marine heat waves. Whether one can cause the other or not, I do not know.
Okay, thank you. And I also have a question, Ronan. There are many works working describing the heat waves affecting health over land, etc. And now we start to have a lot of work focusing on the marine heat waves. So do you think that so what about the knowledge on the relationship between the two, the ocean and the land heat waves? Is there any link? Is there something that we can do?
I think that is a topic that is ripe for new research, because there have been studies on specific marine heat waves which have linked those marine heat waves to the same drivers of nearby land-based heat waves. So there is indeed a co-occurrence, but understanding whether one influences the other or whether there's some sort of feedback cycle is yet to be done. And I think that's a very interesting question to do. For example, I'm thinking if marine heat waves below the surface are easier to predict, as we've shown, and you can have a good prediction on them, that might act as a source of skill for near coastal land-based heat waves. There's speculation, but there's important work to be done there, I'd say.
Okay, thanks a lot. I think that, well, you already answered tens of questions. We are more or less at 50 minutes. I would say that we can close here. No, I see another one from Stefano, last one. I didn't quite understand. I didn't quite understand whether in the end you decided to forecast your marine heat waves in terms of propensity. Is the propensity an integrated signal of number, magnitude, and duration, as we discussed? Do you have to read it again?
Yes, no, it's fine, it's fine. I believe so. We didn't, not doing it by propensity would be looking at the day-to-day skill, the skill day by day into the season, and understanding what, if on a particular day we can calculate or capture marine heat waves. That would be a tough task for a seasonal forecasting system. I believe it's in propensity because we are using the equivalent of seasonal averaging for marine heat waves, so looking at seasonal characteristics, so the number, the strongest intensity event. So the point is, we're not saying, for example, when the strongest intensity event will occur in the summer. We're just giving the magnitude, which may not be fully useful to stakeholders, but it is within the realm of the job of seasonal forecasting, I think. So I would consider that propensity, yes.
Okay, So Ronan, thank you again. Thank you, everybody, and see you for the next webinar that will be communicated through our channels. Thank you. Bye-bye.
Thank you, everyone.